Good afternoon, everyone. My name is Daniel Bikowitz. I'm the team lead on SecureGPS. With me are Helen Gomez, Nahamin Bar Israel, Omar Alali, and Matthew Clayton. SecureGPS is a real-time GPS spoofing detection system we built for our senior cybersecurity capstone. The idea behind it is pretty straightforward. GPS spoofing is a real attack that is growing, and there is almost nothing out there right now that can detect it without requiring you to replace your hardware. We wanted to fix that. Over the next few slides, we will walk you through the problem, how we built the system, and then do a live demo where you can see it catch attacks in real time.
So, GPS spoofing. At a high level, it is when an attacker broadcasts fake GPS signals to make a device think it's somewhere it's not. The location, the speed, the time, all of it can be faked. What makes this particularly concerning is how cheap it is to pull off. You can buy hardware for like $300, such as a software-defined radio off Amazon. And the reason it works so easily is that a civilian GPS signal has no built-in authentication. There's essentially nothing that the signal can prove it came from an actual satellite. So any signal that is stronger wins. The real-world impact is already happening. There was a major incident in 2017 where cargo ships in the Black Sea had their GPS position spoofed. Some of them were showing up miles inland, and this is not just a military problem. It affects fleets, rideshare platforms, autonomous vehicles, drone regulations, anything that relies on a device knowing where it is. The gap we identified is that there are no affordable software-only solutions for detecting this. Enterprise tools exist, but they require hardware changes. We built something that runs server-side, works with GPS, works with any GPS device that can send telemetry over HTTP and does not touch the receiver at all. So here is how it works at a high level. With the GPS devices, we simulate 8 drivers in our demo, send their telemetry to our backend over a simple HTTP post. The payload is just JSON, a device ID, a timestamp, latitude, longitude, speed, and HDOP. The backend is a fast API application running in Python. When a reading comes in, it runs through 4 independent detection checks, which we'll cover in the next slide. Based on these checks, it assigns a severity level, critical, high, medium, low, or allow, and then assigns the events with an HMAC SH256 before writing it to SQLite. That signature piece is something I want to call out specifically. Every event gets cryptographically signed at the moment of ingestion. That means if someone edits the database after the fact, we can detect it. It turns a regular event log into a forensic audit trail. From the database, everything flows up the SOC style dashboard, which pulls the API every 3 seconds and renders everything in real time. The map, the alert, the feed, and device profiles. On the right, you'll see the tech stack. Fast API, SQLite, leaflet.js for the map, and standard Python crypto for HMAC signing. No third-party security libraries. Everything is custom.
The detection engine has 4 methods that run independently on every GPS reading. Speed detection uses the Haversine formula to complete the real-world distance between consecutive points from the same device, then derives the speed. If it exceeds 60 meters per second, roughly 135 miles an hour, it gets flagged. The reason spoofing triggers this is that a spoofer can jump a device's apparent location instantly, Miami to New York City in 4 seconds. This is an example that you will see in the demo that comes around 2,500 meters per second. Geofence validation is another one. This checks whether the reported position falls inside the defined operating zone. Ours covers South Florida and the Miami-Dade area, which is all of our simulated drivers, where all our simulated drivers are supposed to be. Anything outside of this authorized bounds gets challenged. Another one is HDOP anomaly. This one gets a little bit more subtle. HDOP is a quality metric built into GPS data. It reflects how spread out the satellites are that your receiver is currently seeing. Real world readings are typically between zero point 0.8 and 2.0. When you have a spoofer broadcasting from a single point, it generates an unnaturally perfect signal, and the HDOP drops between zero point 0.5, and that's the flag. Another one is bearing reversal. This looks at the direction of the travel between the consecutive points. If a device appears to reverse direction more than 160 degrees while also moving at a highway speed that is physically impossible, it automatically gets flagged. The speed gate there is very important because without it, you would get false positives on parked or slow moving devices. If two or more of these triggers on the same reading, severity escalates to critical. It'll if two or more of these trigger on the same reading, severity escalates to critical automatically.
The dashboard updates live and shows everything clearly. In the center, the map uses green marks for normal readings and red marks for alerts. The green box shows the allowed G-force area. On the right, there is an alert feed that shows this safety level, and it can be filtered by bending it. The system also groups alerts that arrive within 1.5 seconds, so the screen does not get flooded during an attack. Another important feature is the verification page, which is checks the HMAC signature to make sure the event data was not changed. If someone edit or that record, the system can also detect it. Analysis can also review alerts, leave comments, and acknowledge many alerts at once.